Okay, let's see. The electric potential changes from minus 127 to minus 682 when we move 92 meters to the east. Oh dear. Got to draw a picture. Okay, so here's the west, here's the east. And we go from minus 127 volts to minus 682 volts. Okay, so what's going on here is that we are moving, I guess, toward the negative, right? We're getting to a place where it's more negative. This side is more positive. Okay, so we know that this, I'm going to make this direction the positive direction, this direction the negative direction, just because left is negative, right is positive. But we know that this electric field is going to be to the right. It's going to be east. Okay, but let's figure out using our formulas. Okay, what is the magnitude and direction of the electric field? So we're going to use this guy. E is the opposite of change in electrical potential over R. Okay, so our change, remember, change is always final minus initial. Okay, so this is our final, that's our initial. So this is going to be the opposite of negative 682 minus a negative 127, and then divided by 92 meters. Okay, but we're going to move to the right. We're moving positive 92 meters. Okay, we can do this. Opposite of parentheses, 682. Whoops, it should be negative 682. Minus negative 127 divided by 92. And that is, believe it or not, that is a positive 6.0326 newtons per coulomb or volts per meter. So that means it's to the right. To the right would be east. So 6.03 volts per meter east. Remember, a volt per meter is the same as a newton per coulomb. Okay. What is the magnitude and direction of the electric field? So we just did that. What force does it exert on a negative 390? Well, it's going to be the left, but let's figure that out, right? E is F over Q, so therefore force is EQ. Force is equal to EQ. That's equal to, see? Okay, so that's negative 390 times 10 to the minus 6th times positive 6.0326. Let's do it. Times negative 390 E minus 6. And I'm getting that it is negative 0.002357 newtons, or 2.35 millinewtons. Because remember, a milli is times 10 to the minus third. 1, 2, 3. You can put it right there. Okay, so a milli is, all right, so let's see, we've done that. So let's see, I guess we'd have to say, let's go, that would be millinewtons to the west. West. I'm just going to go W. To the west. All right, where are we? Okay, so we answered this. Okay, so we got that answer. We got this guy, right? What would be the change in potential if we moved that charge 15 meters to the west? Change in potential energy, not potential, but potential energy, which, by the way, that's going to be the work, okay? So there's two ways to do this. We could multiply this force by that distance and get the work done, and that would be the change in potential. Let's use the field theory equations, and then I'll do that as like a exciting final step, okay? So our field theory equations would say this. Work is charge times change in VE, and the change in VE is the opposite of E times delta R, okay? And that's from this equation right here, okay? So we got to do this first. So our Electric field is 6.0326. So the opposite of 6.0326. Okay, and then we're moving it 15 meters to the west, and that's in the negative direction, right? So times negative 15 meters. So notice, by the way, we're moving it toward the positive side, so our change in voltage is going to be a positive change. Okay, and that's going to be this minus sign, by the way, is the minus sign from the equation. Okay. Okay, so I was just trying to figure that out myself. Okay, so 15 times this guy is 90.489. And that's positive, okay? Then we're going to use this guy here. Work is Q delta VE. And our Q is the 390, negative 390. Okay, our delta VE is positive 90.489. So times negative 390 E minus 6. And this is negative 0.03529 joules, right? Or negative 35.3 millijoules. In a world where people understand that milli means times 10 to the minus third. Okay, now I said there was another exciting way to do this. The change in potential energy will be the work. Work is force dot distance, right? This force is going to be in an opposite direction. Right? We're moving it to the west, but since it wants to go to the west, we would exert a force to the right. So we're going to get a minus sign with the dot product. It's going to be the cos of 180. And so we just go force, which is, let's see, 0.0023527 times 15. Let's just try it. It should work, right? 15 times that guy. Hey, look at that. I'm getting negative 0.03529 or 35.3 millijoules. Okay, now the minus sign is a little more subtle here. We have to go back to the notion that if I'm taking a negative charge and we're displacing it this way, but we're exerting a force on it that way, right? The work is F dot S, which is Fs cos theta. There's an angle of 180 degrees between the displacement and the force. 180, the cos of 180 is negative. So, you know, we're going back into work energy stuff there. Anyway, hope that helps. These are tough problems.